The general theory of relativity is one of the most important scientific theories of the 20th century, formulated by Albert Einstein in 1915. It fundamentally changed our understanding of gravity and space-time. Here's a breakdown of its key concepts. Space-time, the fabric of the universe. According to Einstein, space and time are not separate entities, but rather a unified four-dimensional space-time continuum. Instead of thinking of space as a flat, static stage on which events occur, Einstein proposed that space-time can bend and warp in response to mass and energy. Gravity as curved space-time. Prior to Einstein, gravity was understood through Newton's law of universal gravitation, which viewed gravity as a force between two objects. Einstein revolutionized this by describing gravity not as a force, but as the curvature or warping of space-time caused by mass and energy. Large objects, like the Sun, bend space-time around them, and this bending affects the motion of smaller objects, like planets or light. A helpful analogy is a rubber sheet. Imagine a heavy ball placed on a stretched rubber sheet, causing a dip. Smaller objects on the sheet, like marbles, will roll toward the ball due to the dip. This is how planets move toward the Sun due to the curvature of space-time. The equivalence principle. One of the foundational ideas of general relativity is the equivalence principle, which states that there is no observable difference between acceleration due to gravity and acceleration due to motion. For example, if you're inside a spaceship, you cannot tell whether you are experiencing gravity, like being on Earth, or simply accelerating upwards in space at the same rate. This principle led to the idea that gravitational effects could be understood as the result of the curvature of space-time, rather than as a force acting at a distance. Time dilation and gravitational time slowing. In general relativity, time is affected by gravity. Time moves slower near massive objects. This phenomenon is known as gravitational time dilation. For example, clocks near the Earth's surface tick more slowly than clocks in space, where gravity is weaker. This effect, though tiny on Earth, becomes noticeable near more massive objects like black holes or in strong gravitational fields. Black holes and singularities. When a massive star collapses, it can create a black hole, an area in space where the gravitational pull is so strong that not even light can escape from it. Singularity. At the very center of a black hole, space-time curvature becomes infinite, creating a singularity. This point represents a breakdown of our understanding of physics because the laws of physics as we know them cease to function normally. Gravitational waves. One of the most fascinating predictions of general relativity is the existence of gravitational waves, ripples in the fabric of space-time caused by accelerating masses, like merging black holes or neutron stars. These waves travel at the speed of light and were first directly detected by the LIGO Observatory in 2015, providing strong evidence for the validity of Einstein's theory. The expanding universe. General relativity also provides the framework for understanding the large-scale structure of the universe. It explains phenomena like the expansion of the universe and cosmic background radiation. Einstein's equations of general relativity predict that the universe is not static but expanding, a concept that was confirmed by the discovery of the redshift of galaxies by Edwin Hubble in the 1920s. Curvature of light. General relativity predicts that light can be bent by gravity. This phenomenon was famously confirmed during the 1919 solar eclipse, when light from stars passing near the Sun was observed to bend, as predicted by Einstein. This bending of light is known as gravitational lensing and is used today by astronomers to observe distant galaxies and objects in the universe. In essence, the general theory of relativity shows that gravity is not just a force but a result of the bending and warping of space-time caused by the presence of mass and energy. It has profound implications for our understanding of the universe, explaining everything from the motion of planets to the behavior of light near black holes. This theory has been verified through numerous experiments and observations, and it remains one of the cornerstones of modern physics, influencing fields like cosmology, astronomy, and even technology, such as GPS systems.